Okay, so thank you, Mani, and thank you, Mamta, for asking me to, well, actually, you forced me to talk on this topic, which is going to be biased because data collection and how we collect data is always dependent on the users. Okay, so this is, so I've taken slides from a lot of other people's also because it's always useful to talk to others and find. And I particularly focus only on single particles, not on how you collect tomographic data, which is very similar, but there are some differences. So now, when we talk of data collection, the first thing that comes to mind is what kind of microscope do we use? So here is an example of a standard grid, which was taken in the microscope we have here. And you can see that the resolution here goes all the way to about 1.4 or beyond. So what I want to say is that the microscope is always good. It's always a sample which limits the resolution. So that's something you need to keep in mind in choosing either what kind of microscope. So always a microscope that is stable in terms of beam and the stage and a good vacuum and all the other accessories like good detector will give you best data. So in single particle cryo-EM, I believe most of you will know it's very simple. We have a 3mm EM grid which has this mesh here, and each of these mesh will have this regular arrays of holes. So carbon is here and these are the holes. And when we put our sample here, 3 to 4 microliters, and then you remove excess fluid, then the hope is that when you freeze rapidly in ethane, these holes will form a thin film of ice and you have your particles there. And the next step is to image each of these holes where you will have your particles suspended in ice. And when electron beam pass through, you will get a projection image, which is what we collect. The biggest advantage in single particle cryo-EM is that you don't need crystals or you don't need to label the protein, unlike in other techniques like X-ray or NMR. In principle, you need very little protein, but sometimes you may end up doing a lot of different things. And one of the major advantage I see is that because we freeze rapidly in ethane, you can get multiple states from a given solution. And also you can tackle heterogeneous samples. You can have either compositional or conformational heterogeneity, which can be separated later by computational methods. So this is kind of a simple workflow which Mani mentioned, one of the enzyme which I worked long ago. So here is a micrograph which shows particles. Some of them are marked in red rectangle. And when you do classification, you can start seeing already the shape and the high resolution features of this molecule. And the idea in processing is that we need to determine the orientation of each of these particles. You get a 3D map. Depending on how good you determine the orientation, you refine, reconstruct. In the end, you get a very good map which you can use to interpret. So this has made things very easy. So if you go to EM data bank in EBI, you will see that this is something I took 2 days back. You will see that the number of entries released by Cryo-EM has been growing exponentially. Here you can see that it's about 50,000 now. And just in 2025, you can see that it's already reached 10,000 maps. So this can be sometimes misleading because if you have, for example, a ribosome structure, it may have multiple different states or maps. So it could be one sample giving you 10 different maps or 10 different entries. So although it looks nice and we can brag that Cryo-EM is helping, so this sometimes can be misleading. But what is impressive is the resolution here. You can see that now from 2005 to 2025, you can see here the 3 to 4 angstrom resolution maps have increased quite a lot, and a lot of structures are now being determined below 3 angstrom, which allows you in many cases to model water molecules which are essential, for example, in drug discovery or in explaining how the mechanism of an enzyme or a protein works. So one of the important thing which is very critical in data collection is this particular parameter is the number of particles which is required to get a given resolution. So there has been a lot of different criteria by different people. So now the best one is about 800 particles, which was estimated by Richard Henderson in 2016, 2017. So we are still far away from this. And this is mainly because of this, what we call as the B factor, which is a combination of the image, the B factor in the image, and how accurately we orient or we can determine the orientation of the particle, which is B computation. So these two together contribute to this, which limits the resolution we can obtain, and the number of particles which we use typically in a structured dimension of a project. So if you look at some of the articles that are published, you will find that there's a big workflow where they start with possibly millions of particles and maybe hundreds, 10,000s of images, and then eventually when you end up in a map, the final map may have only 1/10 or 1/20th of the initial particle that was started. That's mainly because of the B factor which is coming from these two. So this is one important criterion that needs to be remembered when we set up for data collection. And this is one example which Swati, who was my student, we did for one of these enzyme, where you can see we calculated different number of particles and what kind of resolution you get theoretically as well as experimentally. You can see that up to 2.4 angstrom there is kind of good correlation, but beyond that you need a lot more number of particles. That's mainly because we are hitting Nyquist here, which I will explain later. So this is one popular example, upper ferritin. You can see here we started with about 4.7 angstrom. This is in the late 2010s, I think. And now we have about 1.1. This is outdated. There is about 1.1. The critical thing here is, apart from the resolution, is the number of particles. Here you see the number of asymmetric unit because it's symmetric. So it's the average of 24 times. So you see 10 to the power 5, and here we have 10 to the power 7. So that is the number of particles you will need to reach for a very stable molecule. You can see that it's a lot of work, but it's very interesting to see that you can see hydrogens and the holes in the aromatic ring. So this is where we are now. So for very good molecules which are very stable, you can get very high resolution data. So what are the steps in data collection? Let's say if you have a very good sample, the first step is to load your sample after freezing, either in a side entry folder on a 200 kV or 120 kV microscope, or on an autogrid onto a cryos. So once you have the sample, then one has to decide which detector. This is mainly up to the users. They generally go by literature and they go for one of these, which is shown here. Most popular is the K3 because it's faster. And then after you choose the microscope, you have to set the optics in the microscope so that we get the best out of the imaging or the data collection time. So that includes some of this, which is C2 aperture, spot size, beam size, dose, etc. And once that is decided, we have to align both the microscope as well as the energy filter if energy filter is present. And without this, sometimes you can collect a lot of data and it may hit a wall and you will be stuck with certain resolution, and there may be something which is hindering in terms of achieving the best resolution. So once this is done, you set up data collection. Here we go for optimal grid. So you can load up to 12 grids on a cryos, or on a geol microscope 3 grids. So you can get you choose the best grid, and then once you choose the best grid, you go for good grid squares, which is the most important, because even if you have a good grid and if the grid squares are not good, here when I talk about optimal grid squares, it's the ice thickness for a given sample that is very important to get high resolution. So the sample preparation still remains the major important thing in cryo-EM. So here in this diagram, we have this conventional method where you have the grids which are made of support. The support foil is typically carbon. The base could be any of the metals, copper, nickel, molybdenum, or gold. You choose one of these, then you put your sample, you use the filter paper to blot, and then you freeze in liquid ethane. This is the conventional way which was developed by Jacques Dubochet in Heidelberg. This is still most commonly used, but the new methods include, instead of using carbon, one can use gold ultrafoil, or nickel titanium alloy, or titanium silicate film. The base could also be the same or different. Then instead of doing blotting by filter paper, you can use microfluidic spraying or self-picking grid, etc. So there are many different ways to make it. And even plunge freezing now, instead of plunging, you can also freeze by using a jet of liquid ethane so that it freezes fast. So some of these, the way of freezing, comes also from X-ray crystallography, because this is jet freezing, or using a jet to freeze is known for crystals in X-ray crystallography. So the most common is this conventional way. You have a Vitrobot, you just go, you do it very fast. You can freeze the grids in maybe 20 to 30 minutes. And one important problem that you will encounter very often is what we call prefer orientation, and this because of air-water interface. When you put a protein sample or a macromolecule with DNA or RNA, when they encounter the air on the water, where they are suspended, they could adopt something like this, where they preferentially orient, and this could be a big problem. And this can be mitigated by using a thin support, either a carbon support or a graphene, or you can also tilt the state so that you can get different views of the same molecules. So there are a couple of examples which I took, which are there in this review, which we wrote in 2016, where you can see here the catalase, where the center here has no ice, and then the particles, they tend to adopt one particular orientation, and here you have thick ice, and then you can see different views. But in some areas of the grid, you can see that they tend to form these pseudo-crystalline arrays. So this is not ideal. And if you try to process, you will get some map, because we know how catalase looks. It looks like it is correct, but it's very difficult to interpret. In particular, if you are working on a new molecule and if you have a preferred orientation or anisotropic resolution, then it may be very tricky to interpret, in particular, whether it's an alpha helix or beta strand. So this is an important thing. There are multiple ways one can overcome this. One of the easiest thing is to add a detergent. Here for catalase, we tried with Chapso. You can see with different concentration, you can see the number of particles. And there are ways to identify whether you have a preferential orientation or not. This is one way, which is called estimation of orientation determination, UOD, or after you do the reconstruction, you can also calculate by using this 3D FSC. There is a server which is in Salk, which you can use to determine. So if you are using CryoSpark as the image processing tool, it also has a module where you can do the orientation diagnostic. It gives a lot of different parameters. So one thing we were surprised to realize when we were looking at this thing is that even the presence of tag will affect the orientation distribution. So this beta-gal, which is again a commonly used protein enzyme in Cryo-EM, with and without tag, does affect the orientation distribution. You can see here with the tag, the resolution was about 3.2, and once we remove the tag, we got more orientation and higher resolution. So in this case, because it's symmetric, the tag didn't make a big, with or without tag didn't make a big difference. But we have noticed in other proteins where they are asymmetric, then if you have a preferred orientation, then you can't get this kind of high resolution. So in sample preparation, to move away from this preferred orientation, now we can think of multiple different parameters. One is ice thickness, the air-water interaction, which affects this property. You can use surfactant. The property of the surfactant helps. Temperature, affinity tags, and what kind of grid hole geometry do you use. So very often the smaller holes, because they are packed together, they tend to give better ice and probably better data. So these are things which one can try. So now let's say that we have got a very good grid, very good sample. Now the next thing is to look at the microscope, and we get the best of the microscope. So this is a cartoon diagram made by my former colleague in Cambridge, Giuseppe. So here you can see you have the source here. So typically we use a field emission gun. So now people are also getting good data with Lab 6 filament. And the accelerator or the voltage is typically between 300 to 200 kV or 300 kV. And when one thinks of alignment of a microscope, you always start with the top and then you go all the way to the bottom. So there are many things one needs to align. The first thing one tends to align is gun tilt and shift, making sure that the beam is passing through the right axis. And the spot size, which determines whether you get a brighter beam or not, is the C1 lens. Then you have the intensity, how much dose you want to put on the sample is controlled by the C2. And if you have a higher end microscope, you have a third lens called condenser 3 that makes sure that your beam is parallel. However, if you don't have a third condenser lens, the way to make the beam parallel is to expand it so that you are always in the parallel range. So this is important because it will affect your resolution in the end. And we have to, so there are stigmators which are magnetic or electromagnetic coils which tend to make your beam. So if you have some astigmatism, you can correct using condenser or objective stigmators which are controlled. Here you can see the panel using multifunction X and Y. And you focus using the objective lens, so you need to get contrast. The samples we work are all with light elements, so if you want to see them, you need to have a little bit of contrast. That we do by modulating the current in the objective lens by increasing or decreasing, but typically we decrease it so that you get under focus, and that happens here. And then you get magnification and all the way to the detector. Okay, so these are some of the things in the microscope. So as I said in the first slide, microscopes are always good, and the modern microscope, typically we don't have to do a lot. They are well aligned, and if you keep them aligned, they stay like that for a long time. Even if you come after 6 months or a year, very often you will find that not much has changed, and they are very stable and they stay good. So with these new microscopes, all you have to do is possibly correct only the objective astigmatism and maybe some of the beam tilt. Otherwise, there is not much to do. This is what I have seen, but it's possible that sometimes you will have to correct other things like gun tilt or C1, C2. That's very rare. So first thing, we are starting from the top. So from the, let's say the beam has passed through, here we have condenser astigmatism. So this is known, very easily seen when your beam is not circular. So if you have a kind of elliptical beam, then you use this condenser stigmator to make it round. So that you do by deflectors, and you make this round, and this is essential, otherwise you will get. So one thing I forgot to mention is that the lenses in electron microscope have a lot of aberrations. So they are not perfect, and most of the aberrations, some of them we can correct, some of them you can also correct by computation. So the idea in during the alignment is to make sure that we minimize the aberrations, and so we get the best images. So we start with first here with the condenser stigmator to make the beam circular. So that's condenser astigmatism. Then there is one important thing called beam tilt. So when the beam is not parallel to the optical axis, so this is the optical axis, this is like an imaginary line. So if it's not parallel and if it is tilted, then you will have beam tilt, and that will affect the resolution and interpretation of your map also. So the beam tilt can be corrected by two ways. One is called rotation center, the other is called comma-free alignment. And I will show the comma-free alignment in the next slide. So here is before, so this is if you are using one of the thermofisers or even serial EM, how we do comma-free alignment is using a live camera. You defocus the image, not very highly defocused, but reasonably enough that you see the tone ring. And when the beam is tilted here, plus and minus 5 milliradians, both in X and Y direction, the idea is that in both this plus and minus in X or in Y, your tone range should be the same. So that's the idea. So this is what we start with. In the end, after you correct for the comma or you adjust it, then you will see, for example, if you look at here, so this was slightly different to this. Now after correction, you find that they are similar. So that's the whole point of doing this comma-free alignment. And this is now also automated. There are software within the EPU in thermofisher microscope where you can do this correction. And one important thing is that the automated software always try to do something. It is always useful for you to check whether it has done properly. So we have found sometimes that it does something and you will find that that's not correct and you have to go back and do. So what happens if you have some beam tilt? How will it affect your image? I will give an example which we found in one of our data sets in a couple of slides later. The other important thing is the astigmatism coming from the objective lens. So here is an image where you have very bad astigmatism, and you can see already in the images how it is. So again, similar to the condenser astigmatism correction, you do the same. And the idea is here, from this elliptical image, you try to make it circular as possible. Okay. So this is again important. This you do after you have done all the alignment, just before setting up the data collection. And sometimes we also use objective aperture. So objective aperture are nothing but a small metal plate with a hole, typically a small hole, and that is useful to get contrast. So here in this example, you can see there is no objective aperture, and if you try to look at these two different images with 100 or 70 micron aperture, you can see that the contrast is getting better, and you can see something sticking out in this particular liposomes. But yeah, one has to remember that because you put an aperture, you will also cut off information, because you are cutting off of the information from the images. For example, here you can see that there is resolution going all the way to 1 angstrom without any objective aperture. But once you put 100 micron, then you can see that all this information is gone. And if you use 70 micron, even more is gone. So depending on the resolution one is trying to achieve, you decide which aperture to use. So can you take images without aperture? Yes, you can. But there is an effect which can happen because we are imaging on ice. It can result in charging. Again, the charging is something I will explain in later slides. Another important thing is the eccentricity, which is where your sample and stage are. I think this is a movie which I hope it will work. Yes, it is working. So your sample is there, and we try to tilt. And the idea is that when you tilt, your image should stay in the optical axis and not move. And if you have an incomplete or incorrect eccentric height for the given sample, then a lot of things can happen. One is that if you set up your data collection and go home, because of incorrect sample height, it will not be able to find focus. It will stop in middle of the night. And the next day when you come, you will find that you have only 50 or 100 images, and then you will be cursing yourself. That's one thing can happen. The next thing is, because of the difference in heights, you can also have on the images, the particles may have different magnification, many other distortion will happen. So it is important that for each grid square, you have to determine the eccentric height, and that has to be loaded when you are selecting in the UPU. Because if you so let's say that you do determine the eccentric height, but you forget to put it in the data collection software, then it will remember something else, and that can also be a problem. So that's very important, the eccentric height determination of each grid square. Okay, so what are the possible issues that can come during data collection? So optimal imaging is something like this, where you have tone rings all the way in all directions, uniform, resolution going all the way to here 0.8 or whatever, but various pathologies you can find. For example, this one is astigmatism. You can see clearly instead of a round thing, you have more like an ellipse. And here you have a drift. So this can happen when you forget that you have to turn off your turbo pump after changing the grid. So this can happen, and this is easily, so in particular, if you are sitting in a different room and setting up data collection not in the same room as the microscope, you may not hear the pump running. But one easy way to check is just check if the pump is on. Then you can also have things like here, which are the cutoffs. So these are very difficult to find where the source is. Okay, so here you have cutoff. You can see that in this particular example, the tone rings in this direction are okay, but here you see that it's tending to cut off. Okay, so this is not an easy thing to find. One has to go through different places and find where the source is, and it can be very painful and can take a lot of time. Let's say that for whatever reason you have to collect some data sets on this. So it happened to us, and this I think is an example. So here are two images of the same beta character series, and when I show this to you, you will find that they are both similar. There is nothing, no problem, right? at least if you have looked at enough cryo-EM images, you will think that they are all good. But this image actually had a cutoff, and in this there was no cutoff. We knew how to overcome that, and when you do the Fourier transform, you will realize what it is. So here I have done two different defocus of the same area. So this is with a cutoff. You can see clearly here that in this direction you can see the tone rings, but here there is a cutoff. But if you do higher defocus, you will be tempted to think that this is all fine. But here there is still cutoff. Okay. And now after this correction, you can see uniform isotropic ring all the way to the Nyquist or to the edge of the detector. And when you do higher defocus, then you can see that it's nice. So how does it affect image processing? So for curiosity and for more like a fun thing, what we did was to process the data set with and without cutoff. And here you can see that the red line is the FSC curve and the resolution is 0.143. With the cutoff, with this number of particles, this is about 3.3, and without cutoff 2.8. Although there is slightly higher number of particles and this has a D2 symmetry, one could argue that this is because of the extra particle, but we have calculated a map at 64,000 and they are in 2.8 comes. Okay, so you can see that even with a cutoff, you can get decent resolution, but probably you will need more particles to reach the same kind of resolution which you get without cutoff. And fortunately or unfortunately, in the same data set, we also had beam tilt. And this became clear to us because it was not going to high resolution. So then in softwares like Relion and Cryospark, now we have provision to correct for aberrations. And one of them is the beam tilt. And here the red curve for this no cutoff data set, it is with beam tilt, meaning the beam tilt is not corrected, where you have 3.6. And this is the value which the program estimates, and once it corrects for those, you can see that there's a big jump from 3.6 to 2.9, and you can see that in the map. And you can also see here there is a big jump after it goes to 0 and it comes back, and that's an indication that there is a beam tilt in the data set, and that can be corrected using computation. What I don't know and I cannot say is how big a beam tilt can the reconstruction program tolerate. Here 0.86 and 1.4 is okay. Let's say if you have a 5 milliradian beam tilt in both, will that be okay? Which I don't know yet. We had done long ago with 2 milliradian beam tilt. That time it was before the time of all these corrections, so it was not clear to us if it had an effect. So to some extent, I think it's correctable. So I wouldn't let during alignment, you shouldn't think that beam tilt can be corrected later, but it's always best to correct it during just before the data collection. Okay, so far we have been talking with images before energy filter. So why do we need energy filter? I think almost all the microscopes now in India, not all, but almost all of them do have an energy filter. The reason why this might be helpful, in particular if you have a thick specimen, is because of this interaction of electrons with the specimen. So we have most of the beam goes through without anything, about 80% of it. Then you have elastic scattering, which is what gives the signal. And then you have inelastic scattering, which damages the sample, and you get radiation damage. And these are other things which come out from the sample. But the filter, what it does is you can use a tune so that some of these inelastic scattered electrons can be removed. And here is this example from Koji Yonikura, where you can see filaments here with and without filter. You can see that they change in contrast. So here you can see barely the filament, but once you use the filter, maybe 20 eV or 10 eV slit, then you can see that the contrast increases. So for thin samples like single particle, if you have a good protein, then this may not help a lot. But if you have a thicker sample and if you have in particular doing tomography, then the filter is very important. So using filter is great, but you have to make sure that you tune the filter properly. If you don't tune, that's going to also introduce a lot of other aberration or pathology. And the stability of the room will affect the filter. So if you have fluctuation in temperature or airflow, then these filters are very sensitive. and they can give bad images. So the tuning of energy filter independent of the microscope is also important, and make sure that the temperature is very stable. Now we come even down where we come to detectors. So until recently, maybe 15 to 20 years ago, we were using mostly the CCD cameras where electrons hit the scintillator, it get converted to photon, and then it comes, we convert back to electrons to get an image. But now with this direct detector, the electrons are directly identified, and so you get better signal to noise ratio. And these also are running in what we call as rolling shutter mode, so you get movies. And there are multiple ways of detecting electrons. The most common are linear and counting mode. There is also super resolution, which is what I call derivation of counting. So in linear mode, when electrons hit a given sensor, all the electrons that are hitting are being counted. The electron signal is scattered. So you don't count each of this electron even, but as a whole, it's very similar to what was done before in film. So this is very fast and useful, but the detective quantum efficiency of the detector is not as high as counting, where each of the electron that is landing on each of the pixel is identified, and the pixel which has the most of electron is recorded as one electron, because it counts each electron's landing in a given exposure. Unlike the linear mode, the signal to noise is better in the counting mode. So these are examples of typical curve, which is detective quantum efficiency against the fraction of Nyquist or spatial frequency, where you can see that the DQE, which is the amount of signal that is coming in and amount of signal that is going out, is higher at the lower frequency, and then it kinds of goes down at higher frequency. So this is normal. So the idea is that one day in Cryo-EM, we will have a detector which is like this, where it doesn't fall and it will stay very high even at higher spatial frequency. So now you can be surprised that, oh, K2, which is my favorite detector, is like this here. So Greg has made some mistake, or Falcon 3 is better. It doesn't matter, because the way you calculate and the faster whether the frequency of the detector, which is faster frame rate. So you can use one of the other, and they are all very similar. So if in case you are worried, I can give you statistics on the same data, same sample where we have collected, which is very similar. But what is more important, irrespective of the detector, is the amount of electrons you deposit per pixel per second. So here is an example which again Greg did as part of this upper high resolution structure with sorts. Is if you use in this light orange here, if you use a smaller dose per pixel per second, you will find that the DQE is better both for Falcon 3 and Falcon 4 than the one with higher dose. So this is very important, and it doesn't matter if it's Falcon or K2 or direct electron detector. So this is an important parameter. So um, which again I will explain in a couple of slides. So the other thing is the Nyquist limit, which essentially tells that if you want to reach, let's say, 2 angstrom, then you have to sample at least at 1 angstrom. So very similar to, like, now you might be hearing what I speak through a headphone, and now, or a CD, if you are listening a CD, if CD exists still, they are always sampled at 44,000 or something around that. But that's, if you divide by half, that's 22,000 roughly. So that's what the Nyquist limit is. It says that image needs to be sampled twice to get the highest resolution. What happens if you don't sample it properly? Then you get something what people call as aliasing, where the signal will come back, and this can lead to misrepresentation of the data. So this is important thing when you set up data collection: what kind of magnification, what is the pixel size, what resolution you are trying to achieve, which is important. So if you want to achieve, let's say, 3 angstrom, then you should at least sample at 1.5. So these are the different detectors in currently that are most commonly used. You can see here the size of the detector. Typically they are 4 by 4. This one is bigger because D64, the pixel size and the frame readout. So this is important for example, the K3 has 1500 frames per second, which means you can expose only for a few seconds, in contrast to Falcon 3, which is only 40, which means you have to expose for a minute. So that slows the data collection down. But the Falcon 4i, they have improved to 320, which we used to compare like this. So if, for example, if you are using K2, you have to expose 8 to 10 seconds. For Falcon 3, 1 minute. For K3, it will be like 2 to 3, and here we can go to 3 or 4. So that's the improvement we have got. And the critical thing in terms of using detector is there are three different things: flux, fluence, fractions. There are three Fs. The first one is the dose rate or flux. These are number of electrons per pixel per second. So it depends on the detector how many electrons you want to aim for. If you use high dose rate, you get lower DQE. Opposite. This was shown in the curve before, where you can see from the Falcon 3 and 4 that the lower dose gives better DQE. And the total dose is called fluence, which is number of electrons per unit area. So this is the total dose that is deposited on the sample. So we use typically between 22 to 50. This can go plus or minus 10. I don't think it will go minus 10, but actually people have collected even more, 60 or 80 also. So for smaller particles, higher dose will benefit because you get more contrast. For larger particles, even lower dose is sufficient to give contrast. Larger particles are viruses, ribosomes. And the fractions is the number of frames in a given exposure. Let's say if you're exposing for 1 second and you want to make sure that you are in this range between 0.5 to 1.5 electron per angstrom square per frame. So this gives about 20 to 40 frames. And because of these frames, you can do motion correction to correct for movement that has happened during the exposure. This improves the image. So if you do less fractionation, you get smaller sized image, lower infrastructure. You don't need a lot of storage and faster pre-processing. But if you do more fractionation, for example, if you try to do 0.1 electron per angstrom or maybe 80 frames, then you will have larger size movie files, slower pre-processing, everything amplifies. You will need a lot of more data storage and kind of slows down. So this again depends on what you are trying to do, and typically this is the range. We generally use at 1 electron per angstrom square, which is good enough for motion correction, and they are decent sized images. So now I also want to mention, which I have not included in the slides, there are also now ways to compress the images so that the file size becomes smaller. That can also be used. Another important thing before you start data collection is collecting gain reference. So there are two things. One is you have this unprocessed image, and dark reference is something, a property of the detector, when there is no beam and you have some noise coming from the electronics. So that's the dark image. So you subtract the dark from the unprocessed, and then you collect a gain reference, which is you have the beam on, but in a vacuum. So you choose a grid square where there is no carbon, there is no sample, just empty square or empty hole, and then you collect an image, you multiply that, you get a gain corrected image. And this gain correction dose has to be close to what you are using. Okay, so this is not the cumulative dose, which is the total dose that is deposited on the sample, but more on the electron per pixel per second. So that's very important. So now we come to automated data collection, where we start using a low mag image, which is called the atlas. Then we go and look at medium mag at grid squares. You center the hole, autofocus, data acquisition. This goes in a loop, and then you get a lot of images. So this is the whole workflow after you have chosen your sample. Optionally, you can also do drift measurement. This typically is not used very regularly, but there is an option to use. So when we center the hole, there are two ways now. We can do accurate hole centering, where you go each hole by stage movement and then you take an image, or faster acquisition, where you, instead of stage movement, you use beam shift to move to different holes and take images. Okay, so here are a few examples of atlases. So you can see here, you can see the whole grid square here, but there is also a fiber here, which came possibly from the filter paper. And this looks also nice. So I have put here question mark. Is this bad? Is this good? But remember that in the data collection, you just need 1 or 2 grid squares. So here you have so many grid squares. So all you do is maybe collect only these 3 or 4 and you are done. You can get a lot of data in it. So even if this doesn't look good, if your squares are good, then that's enough to get good data. So here is another example where in the same grid square, there are different ice thickness. So for example, this is marked as too thick and this is too thin, and you have something which is optimal. So this now we have programs based on AI to pick grid squares or tell you that this is the best square. But intuitively, you can also take images at one of these holes and then try to understand which is the best for your sample. So once you pick the right squares, then the idea is to look at the holes. So for example, now this square looks like optimal, and you tend to avoid all the ones on the edges because there will be crystalline or thick ice. And this one here is because of not proper glow discharging, where something has gone and stuck there. And this is something if you try to take image, it will take, but it won't be very good. So this we call as thick ice. And when you have, like, again, I go back to the example of catalase where you see these are looking good, but if you look carefully here in the hole, this is ice, but here you have central thin area where there is no ice. This is what is reflected. There is no ice and you have the particles here. So this is not a good square to take, although there are particles, and this won't help in many different ways. And now this is an example where you have a grid square but covered with carbon. So these are typically used for things like ribosome, and it doesn't look good, but you can see already in the low mag image that there are particles. These are ribosomes. So what is the effect of having carbon? So these are ribosome particles on carbon or on ice. You can see the difference where on ice it looks very nice, but the problem is that these are prefer oriented, but on carbon they don't look as nice, but you can see already some of the RNA is sticking out, and if you do reconstruction, they will go very high resolution. And apart from carbon, now people also use graphene oxide. This is from my former colleague Christos, where he started using graphene oxide. You can see that they're not single layer, but there are multiple layers. They're covered very nicely. But you can also have areas of graphene oxide where there is no graphene oxide, there is here. If you try to take images, there is none here. You can see the particles here where the graphene oxide is. So this can be already visualized in the low mag, and then you can decide only to collect here and not here in these empty areas. So this can be done nowadays automatically. And this is something very often we overlook. It's the crystalline ice that can happen because when the grid went into the ethane, it probably was not frozen properly. Then you can get this crystalline ice. This is very obvious when you take a low mag image, part of the grid square, where you can see this background here. And if you take a high mag image of one of these holes, then you can clearly see the rings here, which come from 3.6 angstrom, the hydrogen bond between the water molecules in ice. Okay, so this is also tells you that your microscope is working well, there is no drift, the resolution is good. So even if your sample is bad, if you get some ice like this and if you get images like this, then you know that everything is working fine. So there are many data collection software. So UPU, which is called out of many, there is one. This is not open source. This is licensed by Thermo Fisher. There is high degree of automation. I can still remember when they launched this in 2013, it was very difficult to use, but now it has become so easy to use. It also has inbuilt comma-free and astigmatism correction, and it also can do aberration-free image shift, which I will explain. And there are also now EM multi-grid smart grids, with meaning you can load all 12 grids, you can ask it to screen, and then you can choose which one you want, and there is also now quality monitor. So apart from this particular software, there is also serial EM, which is open source, adaptable. It gives you the flexibility to do a lot of different things. You can write your own program, and you can also do a lot of things. And there is Leginon, which is open source, and Latitude is licensed through Gatan or Amtech. So these are few. There are many people all computer software people, they tend to write their own. So it's not needed. If you like one, please use it. So in the EPU, this is how it looks, Atlas overview. Users can select squares, or there is also automated square selection. This is the first step. In the next step, you go to one of these squares and then you pick the holes. So because the quantifiers are C flats, they have regular arrays of holes. You can just tell that these are the hole size and this is the distance, then it will automatically pick. You can also then go back. For example, here there is an ice particle sitting here. So you can remove this or you can also leave it. So user can select or AI can also select it. In my opinion, this is one of the important things, picking the right squares and picking the right holes, which will make the downstream image processing much more easier, because you don't want to throw a lot of images. So if you collect 1,000 images, you would want to keep as much as possible and not throw a lot of them. And that is determined by what you do here. So most of the time, we spend most of the time in selecting the right grid square and the holes. So then the next step is to define where you want to put your exposure and the focus. So here there are six different exposure areas in a particular hole. You can also put focus somewhere here or drift, and then you collect a lot of images. So now, is it okay to collect 6 or is it okay to collect 1? That depends on the users. I will explain why you can use one or the other in a couple of minutes. So the whole workflow when you start this automated data collection, it looks like this. You have the overview of the grid, overview of the grid square and the holes, and then the image that is taken on this particular hole where you can see the particle. And once you set up and you start, in principle, you can go for multiple days. So for example, if you start on Friday, by Monday, if you come, it should have collected log. And it's always useful to check every now and then that it is going on. It can stop for many reasons. One could be software, one could be there is no nitrogen, or one could be because there is no the eucentric height was wrong, it can stop. So it's always useful to check because it's time. Most of the facilities, the time is the limiting factor, so it's better to check what is happening. Now, one important thing when we think about image collection is something called specimen charging. So here we have the carbon and our sample lies on ice. So this is our sample and this is ice. So because ice is ice is an insulator, then you have electron beam hitting. Oh, sorry, the beam is coming. You have charge building up here. And because we have here carbon, there is also charge building up here. And because of this charge buildup, if you have your beam only covering this area, not touching the carbon, then what will happen is you get something called charging. And the images will look very bad. And this cannot be corrected by the motion core or any of the program. So they will remain bad. One way to overcome is to add a carbon or a graphene layer on the top of this ice, and then you can overcome that and decrease charging. Okay, so these are extremely designed to get charging as an effect. We did long time ago, where you can see the viral capsid particle. This is an image where the beam is very small, but it doesn't show any charging. But this we did with a particular setup of condenser aperture. But once we remove that, you can see that the same area, the same hole, now you have charging. So you can see the particles barely visible, but you can see that they're kind of what looks like drift. So if you try to correct it, it won't correct and it will remain the same, or maybe some improvement will be there. So this is extreme case of charging. So how do we avoid charging? One way is to eliminate the beam uh, bigger than the hole so that the beam touches also the carbon. And then the other way is to use objective aperture, where you have an aperture which will remove some of the electrons and let some of the electrons go so that it neutralizes charging. So these are two ways to avoid charging. And people who have used plastic sections in room temperature electron microscopy will know that objective aperture is essential. Otherwise, the film or the plastic which you have put, it will just move or it will just vapor. It will just come apart. So using aperture is very important. So I think I'm going beyond time, but I'll just finish fast. So so the importance of beam size will affect charging. So if you have one image covering the whole hole, then you have less charging and you get better quality. But if you try to do something like this where the beam is not centered and off centered from the hole, then you get more charging. Or if you use two beams or multiple beams, then you get more charging. So although it looks like you get a lot of images, that the quality will be less. Now, in the images I showed where there was charging, you didn't see that there was fringes. So this comes from the FEG because it's very coherent, and this is because of the condenser aperture. You see these fringes. So now let's say if you are condensing the beam and if you are trying to take image like this, then because we are doing single particle, these fringes will come and this will affect the area. So why? So to overcome this, what Thermo Fisher has done is what we call a fringe-free imaging, where you remove this fringe by changing the Z height of the stage so that these fringes go. So this allows you one to make this beam very small, and then you can take multiple images. So for example, using this small beam, now you can collect here 8 images. So if you do that in a particular grid square, then you get possibly 8 times more. So this is what we call as fringe-free imaging. And the way you can collect data is conventional and faster data acquisition. Let's say that you have fringe-free imaging. You move the stage from 1, 2, 3, 4. So that will also work. It will collect a lot of images. So it has less aberration because you're moving the stage, better centering because each time you move the stage, you center the hole. But because of stage movement, you have lower throughput and lesser number of images per hour. So in faster data acquisition, the same thing applies. Instead of stage movement, you just move the beam so that here you center once, then you don't move the stage, move the beam. It goes like this. So you get more images per hour, maybe 2 to 3 times more or sometimes higher. But because we are moving the beam, you can get aberrations. And now again, because there are programs within Relion on Cryospot which can deal with it. So you can uh, group each of these images coming from this based on parameters that comes from the metadata. You can group them and individually determine the beam tilt and other aberration parameters so that you can overcome these aberrations. So in kind of summary, what are the data collection parameters that typically one uses? So depending on the detector, you tend to use flux or dose per pixel per second. If you are using K2, that's between 4 to 8, K3 is 10 to 20 and so on. The fluence is the total dose per sample is 20 to 60. And then you have frame, which is 0.5 to 1.5. The defocus range, typically people use 0.5 to 2.5 plus minus 0.25. And this is again important and depends on the kind of sample you are looking. So I give two examples, one at about 9,000 angstrom as defocus, where you can barely see the particle. So here still we can see the particles, computers can easily pick. Very high defocus, we can clearly see. So if you are starting with a new project, it's always good to start with higher defocus where you can see particles. Then you can go to low defocus. Why you need to use low defocus is something that will take a lot of time. Maybe in another lecture, somebody will explain. Uh, the another important thing which we take for granted is the good vacuum that is needed in the microscope. So here is an example of same image taken roughly about 12 hours later. So this is before and after. You can start seeing that the what we call as leopard skin, where the eyes starting to contaminate. So in modern microscope, people think that you can leave grids for about a week, which may be possible, but typically 2 to 3 days is pushing, and maybe in the fourth day you start seeing, then you may want to change grids. So actually you can still collect because particles will be visible, but the quality will go down, so you will need more particles. So vacuum is an important thing, and cryo cycle every 3 weeks is important so that all the moisture is gone. So to summarize, so here is a diagram which tells a lot about this. You can see in this review where now we have different kinds of source starting from FEG, which is commonly used. People do have now monochromator as well as cold FEG, which is more coherent. And then we have different way of data collection using aberration-free image shift or fringe-free imaging, different detectors, energy filter, and so on. Irrespective of what is there in the microscope, the critical things are you need to have your specimen at not eccentric, eccentric height. I made a mistake here. Defocus range is important. Parallel illumination and beam tilt, right choice of the objective aperture. You don't want to cut off information. Minimize charging by choosing the right beam size, right pixel size and magnification. If your sample is not going very high, you don't want to burn your time as well as image processing time by using high pixel size. And always remember, quality is better than quantity. Sometimes you can get very good data even with 200, 300 images instead of 20 or 30,000. And to conclude, so the facility in Bangalore has been supported by the Department of Biotechnology BLife grant, which is in INSTEM, and I am in NCBS. A lot of slides I have taken from Giuseppe, who is in Cambridge, and Christos, who is in EBIC, where money was before. Maybe Christos money overlap a little bit. Sucharita, who is looking after the facility, if you have anything to know about the facility, you can ask her. And these are some of the links which one can look into. There are a lot of information available in the web. Some of the things you will find, for example, this LMB Cryo-EM course, which gets updated every 2 years, has a lot of information, and Grant Jensen's lecture also on YouTube, which tells more about basics of microscopy. And Geol has a glossary of terms, like if you want to know what is off-axial coma aberration or so on, these are all available. Okay, I overshot my time, so I'll be happy to take any questions if you have. I will stop here.
Thanks, Vinod. That was very comprehensive and I think very useful to all of us who are collecting data. So if you are okay, we can take a few questions.
Yeah.
Okay. So I think people can raise their hands maybe, then I can just call out the names. For now, we have two questions on the chat. One is from Prem Kaushal, which is, can you elaborate more on the cutoff parameter?
Yeah, so the cutoff was a difficult thing. So I mean, I'm assuming that you were asking about the beta gal cutoff. So we started seeing when we were taking images and FFT, you saw the cutoff, and we spent like about a week or two figuring out where the cutoff was. In the end, we found that this is happening because of compressed air going into one of the part on the microscope, which was giving some frequency, some cutting off a frequency. So that took us quite a while to figure out. So this is, so initially we thought it was because column walls close and opens, and that's controlled by compressed air, and that's causing. Eventually we changed that, but still it was there. Then we found that the amount of air that is going was causing this. It's like a small hiss, which our air will not be able to find, but that was causing the cutoff.
So only diagnosis would be that we see at low defocus and high defocus. If
no, you will see at any defocus, but you can ignore because you will think I can compensate with number of, more particles or more images.
Okay, yeah, thank you.
Okay, we have the next question is from Imran, who's asking, does the his tag affect overall resolution of in vitro assembled translation complex?
So the tags, not just his tag, any tag, mostly we think it's because of the charge. The tag will affect depending on the protein. So it's very similar to crystallography, where sometimes tags have helped because they tend to form crystal contacts, and tags sometimes have been detrimental because they interfere with crystal contacts. So the similar thing applies. It's not, you cannot generalize that tags will have an effect. But if in case you find very often that there is some problem in your orientation, one of the things to look is tag and make sure that that doesn't affect, or if you remove it, it helps.
So maybe I'll just ask one related question is, does the size of the tag, have you tested that?
Yeah, so we had this spike protein, which is notorious for paper orientation. It's a trimer and it has multiple his tags. So when they come together, so what we think is because of the charge, if you have like 10 his decahistidine tag and 3 of them coming together, then it's a 30 histidine. And if
Yeah.
you have a lot of charge there, then it's going to affect how the protein behaves. I think it's mostly, we think it's coming down to the charge which affects the orientation.
Okay. I think we have one person who wants to ask a question. So Darshan, can you unmute yourself and ask the question?
Yes. So you said that we tend to avoid collecting near the thick ice region, but are there any cases where we collect data from thick ice?
Yes, there are multiple cases. One of the common example is the nucleosome. So nucleosome people assemble using the histones plus the Vidum DNA, and that easily tends to fall apart. In particular, when you have thin ice, you can clearly see that there is DNA and there is protein. So there they found that using thicker ice does help. And there is another example where they use a faceplate and they found that this particular protein also or you get better views in thicker ice. Um, so thicker ice is not a detrimental thing, but if you don't get enough contrast, then it can be a problem. And people have done studies. I think in the literature you can find that the optimal ice thickness will make things easier. Essentially, the number of image and number of particles will be determined by the ice thickness. So if you're for some reason if your protein likes thick ice and you can't do anything else, yes, you should collect probably more, maybe I don't know 5 times more, and then hope that it goes to high resolution.
Yeah, I have a similar case. I work with microtubules, so most of my data is collected around thick ice, especially when we have decoration on the microtubule as well. Otherwise, in thinner, you see like squashing of the microtubule sometimes. So that kind of thing. Okay, I'm swapping between the hands and the chat. So there is in the chat, Aman has asked how to decide defocus value based on ice thickness parameters.
So defocus, as I said, it's the modulation of the objective lens current. You defocus so that your eyes and your brain or our perception is able to distinguish the particle in different orientation in a given image. Okay. So if we are able to tell what kind of orientation, whether particles are there, the computer will easily handle. So that's how so when you are screening, you already try different defocus to see where you get the best contrast, and that's how you decide the defocus.
Okay, so next we have one question from Sangeeta. Is the use of chaps to prevent differential ice formation applicable to all protein samples, or does it depend on the sample type?
Oh, it's not just chap. You can use any detergent. So detergents tend to affect how the ice is formed, and they also play or affect how the protein distributes within ice. So one thought which not everybody accept, but one thought we always had is that for any sample, we suggest use small amount of detergent because it will prevent the protein or the macromolecule getting exposed to the airborne interface, which can also cause denaturation. So many samples don't need this kind of use of detergent like apoferritin or beta gal. They work fine, but there's no harm in adding some of the detergents. So if in case you are worried if the detergent is going to affect the structure, very often not, because we use sub CMC or below the CMC of the detergent, so it will be monomeric, so they generally don't affect.
I think, yeah, Siddhant, do you want to ask your question? You have it in the chat as well.
Hello, Dr. Vinod. I'm asking that the users who come from outside to use the facility, they have very limited time, say 1 or 2 days. So in that case, if we are using Krios, which has 12 slots, so and one protein, so what is the strategy to prepare all the samples? Like, should we do it one by one? Like one by one is not practically possible. So what are the top 10 conditions for one protein sample that the user should make and observe?
So easy answer is that they should make only 2 grades. Because if the biochemistry is good and the protein is stable, then 2 grades mainly because we are doing this Vitrobot and plunge freezing. that also has variation depending on who is doing the freezing and how we blot and how we are handling. So let's say you drop one grid or bend it. So 2 grids is sufficient. But if in case you know already something about the protein, then as I said, one can use detergent or one can use different grid holes or the grid geometry so that you can screen what is the best for that particular protein and decide. Is that answering? It's not an easy thing to tell. Yes, 12 slots is very attractive and you can put 12 grids, but typically I would say, I think I've never made more than 4 grids for a given protein, because within 2 grids, one should know what is the problem or if it's going to work.
Yeah.
Okay,
I think you have
thank you.
to test it and see once
Yeah.
at least, then proceed. Okay, there's one question in the chat from Jyoti. If there are particles which tends to stay on carbon part, then how to prevent more charge deposition while collecting data?
I think I'm not sure about the question. I will try to answer. I think there are 2 things. One is charging. The other one is particles staying on carbon. So for the first one, if particles go to the carbon, not to the ice, one way is to make the grid more hydrophilic by glow discharging longer. Then you will get more particles. This is theory. Okay, more particles on the ice. So that's one way. The other way is to increase the concentration. Again, you can look at the review which me and Richard wrote, and also in the recent catalyst paper, we have a table which tells that if you have a right ice thickness and for a given size of the molecule, what kind of concentration you need so that you can see, let's say 100 or 200 particles per image. So that's a good guide, but that shouldn't be used as like a, the written gold. It's not written in gold because things differ. So particles, if they go to carbon, you try to push it away from carbon by either treating carbon with something or glow discharge. So glow discharge treat the carbon by making it charged. So you can treat with, I don't know, polylysine or amylamine. There are many things. So if I give you a list, there will be like 100 of things. You can't test all of them. But if you know why the protein is going to the carbon, then you can fix that. And to prevent more charge deposition, that's a different thing. That happens only if you condense your beam and put only on ice, then you get charge. So if you are touching the carbon, then it won't come.
Okay, so Rohit Singh, can you unmute and ask your question?
It was a great presentation, sir. I wanted to ask that in one of your slides, you suggested temperature as a tool to solve orientation problem. So how does that work?
Oh, this we found by accident. So typically what happens is we all are protein biochemists. We like to be in cold room, and we always think that our protein is best at 4 degree. And when we go to freeze, we also tend to keep the temperature of the Petrobot chamber at 4 or I don't know 15 or 20, except Mamta, who was using at higher temperature because of microtubule. So this was the idea. So when we were testing, I think one of the protein is that we found at very low temperature it tends to form this aggregate and it forms this pseudocrystalline array. So when we increase the temperature, it started to separate out. And then we realized that that can also be a factor. But we have not tested systematically for a given protein on different temperatures. So we think that that's one parameter we should not forget when testing many things. Temperature is one thing we should remember that it can also affect.
I think there's one last question in the chat, which is from Smriti. What all factors affect CTF fit resolution apart from defocus? How can we make sure most of our data is of higher quality, in bracket less than 5 angstrom CTF fit resolution?
Okay, so that resolution that comes out from any of the program will depend on 2 parameters. One is the ice thickness, of course, because if you have too thick ice, then the resolution that is estimated by the CTF program will be low, and the number of particles, because it's depending on the signal. So let's say if your sample is good, and if your CTF is telling 8 or 10 angstrom, it doesn't mean that it's bad. You may have like 10 particles, 12 particles. I have seen with ribosome, there are 10 ribosome, but because it has thin carbon, the CTF resolution will be 3 all the way to 3, but it doesn't mean that it's good. So those values can be used for selecting good and bad images. What one needs to remember is that for a given data set, let's say if you choose one grid and few grid squares, is the CTF resolution estimated remains similar, not same but similar. Let's say between I don't know 3 to 5 angstrom or 5 to 6 angstrom. But if you go to different grid square because of difference in ice thickness or something else, it may differ. But so within a data set, if they are constant, then that's what one should look for. But not like you shouldn't use it as a way to tell my CTF resolution is 8, so I will not get high resolution. That's not true, because if you have just ice and let's say 15-20 particles, it is not like you are doomed. You will get something. And I have seen in my own example, we have got data below 5 with particles that were like 10 to 15 particles per image, and CTF resolution was low.
Thanks. Sai has a question. Can you unmute yourself and ask?
Hi, Vinod.
Hi, sorry.
How is in the fringe-free data collection strategy, the beam diameter will be lower, isn't it?
Smaller, yeah.
Or is it meant? Yeah. So how is then charge deposition going to be? Is it going to be a bigger problem?
No, it can be bigger. So again, so if you had a thin ice, what will happen is if you have the beam which are smaller, that can actually it can also blast the whole ice. So that can also happen. But in this fringe free, what they do is they touch the part of the beam on the carbon, and because one will use very high magnification, like I don't know 120 or 150, the pixel size will be like 0.5. So the detector area will be very small, the field of view. So some of the beam will be touching the carbon, and some of the detected area will be just focused on the ice or the particle, and that's how you overcome that.
So that's inbuilt in the alignment, is it? That it should touch
No. Fringe free. So AFIS, which is the the beam shift dependent movement of data collection without stage movement, is part of EPU, but fringe free is something one needs to ask for. Right. It's not standard. So that needs to be asked, but it's very easy to set up. So before it was automated, when I was in Cambridge.
If it is set up, then how does, should one take care of the beam diameter?
No, not needed. So no, before it was part of EPU. When we did, I showed one of the images, that with charging, that was done through that, through fringe free alignment, where we manually set it up and then we were using. So it should in principle work. But only thing, as facilities, we are all facilities, we have to make sure that we don't switch between different things very often. So because it takes a lot of time to set it up, and if it's set up, let's say if you use it for 2 to 3 weeks without changing anything, then it should be fine.
Okay. Thanks.
I think there is one question on what is the optimum concentration for ribosome from Imran.
Oh, I don't know. In nanomolar, about 80 to 100, I would think. If you use carbon, so if you use ice, then that will differ. So if you are using thin carbon on top of the holes, then this is kind of the optimal. Okay. Maybe 150 is max.
Okay. And then one more question is from Debayan. Is faceplate still relevant in image processing, or we can create contrast by the use of defocus only?
Yeah, faceplate was thought to be very useful, but people realized that even for small molecules, it was not strictly needed. So this faceplate is one which Radharsteen Danav had designed based on this carbon film. But now, so for that is not very commonly used. I think most of the new microscope don't have the faceplate at all, that faceplate. So we can get away with defocus. But range of defocus which you want to use will depend on the molecule. And again, as I said, that will take another lecture to explain what is the effect of higher defocus, lower defocus, what kind of range to be used. But I know that Thermo Fisher has now a different faceplate using laser. That seems promising. Only thing I was told is that it's another, I don't know, $2 to $3 million. So I don't think we'll get it that easily. Maybe IIT Madras with a lot of money will do.
We'll see. Okay, maybe we'll have the last question from Rohit Singh. Can you unmute yourself?
Sir, I wanted to ask just one more question. What are third order aberrations and how do modern microscope correct for them?
Sorry, can you repeat?
Sir, what are third order aberrations and how do current microscopes correct for them?
So spherical aberration is one of them, and that's not corrected. So each lens has its own, because lenses are not perfect. So spherical aberration is one of them. We have this value 2.7 for many of the TFS microscopes. In principle, you can have a spherical aberration corrector, which can correct for that. A couple of microscopes in the world do have that, 2 in Germany, 1 in Genelia, where the spherical aberration becomes 0. But at least from what I have seen, I don't think it makes a lot of difference. Maybe in alignment, it makes a difference.
Mani, do you have any questions?
No.
Okay. Maybe just one thing, because we all collect data. So if we find after data collection that our microscope is not aligned properly or there were aberrations, in your experience, how much benefit have you seen in resolution using software corrections? And
so
does it?
beam tilt, at least it has helped. Software are able to figure out.
Okay.
And I've tested a lot on that particular data set. By after determination, I reset it to 0 and then found that resolution goes back. So that is something it is able to handle. Other aberrations, so although in Relion it says that don't use this if your data doesn't go, people tend to use this fourth order aberration and so on.
Yes.
I have not tested because I think you need to be at a higher resolution to test that.
Yeah.
And my understanding is that beam tilt is something which affects most rather than the other ones. And maybe at below 2 angstrom, they will also come into play.
Okay.
Up to 4 angstrom, I can tell we had 2 milliradians beam tilt as a deliberate thing long ago. Both data set went to 4 with and without beam tilt. So my understanding was that until 4 angstrom, it doesn't matter, it should work. And below that, everything starts accumulating.
Right.
So if you want to reach below 3 and below 2, then everything becomes important.
Okay, I think that was amazing. And thank you very much, Vinod.
Okay,
for being
it's a pleasure.
first.